In this video, we're using the binomial theorem with negative powers and fractional powers, higher level only. And the difference from the version you already know is not a small one. The expansion stops being an expansion. Here they are side by side. 1 plus x cubed is 1 plus 3x squared plus x cubed. 4 terms, and then it is finished. And it is true for every value of x you could put in. Now 1 plus x to the power minus 1. 1 minus x plus x squared minus x cubed plus x to the fourth. And it never finishes. It runs forever. It is also only true when the size of x is less than 1. Watch what happens if you ignore that. Put x equal to 2 into the second one. 1 minus 2 plus 4 minus 8 plus 16. The running total goes 1 minus 1, 3 minus 5, 11. It is not settling on anything. It is flying apart. And the number it is supposed to equal is 1/3. So there are two genuinely new things to handle here. The expansion does not terminate, and it comes with a condition attached. Example 1 is the version you already know, because that is where NCR from last video turns up again. For a positive whole number n, a plus b, all to the n, is nc0, a to the n, plus nc1, a to the n minus 1, b, and so on, down to ncn, b to the n. Take 1 plus x to the fourth. The coefficients are the 4 CR values, 1, 4, 6, 4, 1. So it is 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth. 5 terms, valid for every x, and then it stops. And hold on to why it stops. 4c5 is 0, and so is everything after it. That 0 is the only thing killing this series. Here's the general form, and it is written differently on purpose. 1 plus nx plus n times n minus 1 over 2 factorial, x squared plus n times n minus 1 times n minus 2 over 3 factorial, x cubed, and so on. Now look only at the tops of those coefficients. When n was 4, that chain counted down. 4, then 3, then 2, then 1, and then it reached 0 and killed everything after it. That is why it stopped. Now let n be any rational number. Negative, a fraction, either. If n is minus 1, the chain runs minus 1, minus 2, minus 3. Counting down from a negative number never passes through 0. Nothing cancels. Nothing dies. The series runs forever. And a sum that runs forever is only worth anything if it converges, which is why this version carries a condition. The size of x has to be less than 1. And here's the trap, which is worth more marks than anything else in this video. The formula is written for 1 plus something. If your bracket starts with a 2, you cannot just use it. So take the 2 out first and carry it as a power outside. 2 plus x to the minus 1 is 2 to the minus 1 times 1 plus x over 2 to the minus 1. And here's the part people forget. The condition moves with it. The something in the bracket is x over 2 now. So it is the size of x over 2 that has to be below 1, which means the size of x less than 2. Factor first, then read the condition off the new bracket. Example 4 does this one for real. Example 2. Expand 1 plus x to the power minus 1 as far as the x cubed term. So n is minus 1. The first term is 1. It always is. Then nx, which is minus x. Then n times n minus 1 over 2 factorial. Minus 1 times minus 2 over 2. 2 over 2. 1. so plus x squared. Then minus 1 times minus 2 times minus 3 over 3 factorial. Minus 6 over 6, minus 1. So minus x cubed. 1 minus x plus x squared minus x cubed, and on it goes. Valid when the size of x is less than 1. Now look at what that actually is. First, term 1, and every term after it is the one before it times minus x. That is a geometric series with common ratio minus x. And we already have a formula for the sum of one of those to infinity. First term over 1 minus the ratio, 1 over 1 minus minus x, which is 1 over 1 plus x. And 1 over 1 plus x is exactly what 1 plus x to the minus 1 means. So the two videos agree, and the condition is not a similar condition. It is the same one. Sum to infinity needed the size of the ratio below 1. The ratio is minus x, so the size of x below 1. Same condition arrived at from the other side. Example 3. A fractional power. Expand the square root of 1 plus x, which is 1 plus x to the power a half, as far as x cubed. N is a half. First term, 1. Then nx, which is x over 2. Then a half times minus a half over 2 factorial. Minus a quarter over 2. Minus an eighth. Then a half times minus a half times minus 3 over 2 over 3 factorial. 3/8 over 6. 1/16. So 1 plus x over 2 minus x squared over 8 plus x cubed over 16. And there is a trap sitting in those signs. Plus, plus, minus, plus. It does alternate, but it starts one term late, because the first bracket in the chain is positive, and every bracket after it is negative. Do not pattern match the signs off the last example. Compute every coefficient. Example 4. The trap, live. Expand 2 plus 3x, all to the power minus 2, as far as x cubed, and state when it is valid. Here is the wrong start, and it is the most common line on a script. Putting n equal to minus 2 straight into the formula. You cannot. This bracket starts with a 2. Right start. Take the 2 out. 2 plus 3x is 2, times 1 plus 3x over 2. So the whole thing is 2 to the minus 2, times 1 plus 3x over 2, all to the minus 2. And 2 to the minus 2 is a quarter. Now the bracket starts with a 1, and you are allowed to expand it. So expand 1 plus y to the minus 2, where y is 3x over 2. The chain gives coefficients 1, minus 2, 3, minus 4. So 1 minus 2y plus 3y squared minus 4y cubed. Now put y back. Minus 2 times 3x over 2 is minus 3x. 3 times 9x squared over 4 is 27x squared over 4. Minus 4 times 27x cubed over 8 is minus 27x cubed over 2. And the whole line still has to be multiplied by that quarter out front. A quarter minus 3x over 4 plus 27x squared over 16 minus 27x cubed over 8. And now the validity, which is the mark people drop. It is not the size of x less than 1. The bracket you actually expanded was 1 plus 3x over 2. So it is the size of 3x over 2 that must be below 1, which is the size of x, less than 2/3. Example 5. And this is what the whole thing is for. Use the square root series from example 3 to estimate the square root of 1.02. 1.02 is 1 plus 0.02, so x is 0.02, comfortably inside the size of x less than 1. Now just put it in. 1 plus 0.02 over 2, which is 0.01, minus 0.02 squared over 8, which is 0.00005, plus 0.02 cubed over 16, which is 5/10 millionths. Add them up, and you get 1.0099505. Now the calculator. The true value is 1.0099504,938. They agree to 7 decimal places. 7, not 8, and it is worth saying the honest number, rather than claiming the series is exact. 3 additions bought 7 decimal places, and the reason it is that good is that x is tiny. Every term here is at least 100 times smaller than the one before it. So, the extended binomial theorem. N can be any rational number. The series does not terminate, and it only holds when the size of x is less than 1. So factor the bracket until it starts with a 1, and move the condition when you do. This is how roots were computed before calculators existed, and it is close to how your calculator computes them now. Next video is the last one in number and algebra, taking one ugly fraction and splitting it into 2 easy ones. Partial fractions.